on, as far as I know. Can you hear me now? Okay. Great. So welcome to the last event of the day for today, except for dinner. We have a discussion panel. I'll briefly introduce the panelists, because if I introduce them fully, that'll take up half the panel. I'll just tell you their names. Jianqing from Princeton, Bin Yu from Berkeley, Peter Buhlmann from ETH, Peter Bickel. I don't need to introduce him. John McAuliffe, who is at Voleon and UC Berkeley, and Tao Shi from Citadel. So what we're going to do is I will start with asking just a few starter questions, but I don't want to be asking all the questions. So then it'll go over to the audience. And I hope you will all have things to ask. So what I'd like to start with is, which is of course one of the reasons we're here, is celebrating Peter's long career. Statistics has grown enormously over the time that he has been active. There are many more topics and people and journals and papers. And what I'd like to ask is, what do you think has stood the test of time over these years? What are the themes that occurred over your careers that are still relevant, that were the most important, that didn't fade into the past? And I'd like to start with Peter. That question.
Thank you. Is this audible? Can you hear me? No. No. No, the mic is off. So how do I get it?
No, this says on. Should be on.
Oh, but he's going to raise the volume.
It takes a while until.
Okay. All right, I'll talk.
This is good. You could put this down, Peter.
I can put it down.
Yeah, it's
All right,
not
good. Where? No, this I need. That's what I need. The mic I want to get rid of. That's what
yeah, you're talking,
No,
you're
because
talking into this thing.
Oh, okay.
So if you just put
Of
it in your
course.
pocket.
Forgive me for my technological incompetence. And also forgive me because I'm going to read just to make sure that I don't freeze up. So first of all, of course, these are my opinions, and they're only largely relevant to theory, because despite some indications of my interest in applications, that's still what I've basically spent my life on. So fundamental changes have occurred in all aspects of society because of the development of technology. So particularly the computer, but also miniaturization and new ways of measuring. And the implications for statistics have been in the amount of data, the types of data, and the feasibility of analyses of the data. The union with machine learning and AI as part of the newly defined field of data science has also come out of that. And this is the I think, reason that we have had this increase in people, journals, conferences, and this particular conference being held under the auspices of the Simons Institute and CDSS. Okay, so now the question about themes. So themes appear, disappear, and reappear during this period under various names and with very different emphases. Stochastic approximation applied to regression has become stochastic gradient descent applied to everything. Sequential analysis is always there, but has a big new center of importance as online analysis of data. There's some larger examples, multiple comparisons. Testing has always again been with us, but has been brought to the fore by the need to make many simultaneous judgments in biology and other fields. Post-selection inference has again always been a concern. You go back to the Chaffee intervals, but there's been an explosion of new work. There have been big thematic changes, as far as I can see. Computational performance has to be combined with inferential performance. So general mathematical descriptions, which are okay in the papers that I originally wrote, in terms of optimization, are not enough. Algorithms need to be at least written, if not necessarily feasible. Randomness has become an essential tool. Again, it's always been present, experimental design, randomization tests, but now I think it's become essential. Monte Carlo, cross-validation, the Gibbs sampler, the bootstrap, and many other things. There are what I view at least as unchanged features, at least in my view of statistics, is that probabilistic models abstraction and representations are still at the base of statistics. To say anything, I think we always have at some level to think of the data as approximately independent, approximately identically distributed structures, possibly conditional on other parts of data or unobserved latent variables. We have non-parametric models have become paramount, but in fact, semi-parametric models are, of course, with us still. And then there's the other axis of Bayes, empirical Bayes, latent variables, and so on. Analysis has remained, I think, really largely the same by approximation and by simulation. Approximation, I view all asymptotic theory, including non-asymptotic bounds, as approximations. There are some new features, though, of course, again, there's been an emphasis on high dimension, on sparsity, complexity as parameters as important as sample size. And the non-asymptotic bounds, which I've always complained about because they're really asymptotic theory without with specification of unknown constants, do give qualitative information. However, the basic questions remain, and I think some of these were alluded to in various talks, but in particular Ben's also talk, which factors covariance matter? Another way, which ones are causal? How far can we extrapolate in causal inference and in prediction? Right, the population can change, and prediction is no longer valid, and of course, in causal inference, confounding factors or factors which you don't know about at all. And then finally, the third point, which I think is really fits with what Ben said particularly, is that we need, can we explain? Can we predict in terms of things we understand? That's remains open, will undoubtedly remain open forever. Because of course, what we understand changes as time goes on. There are themes which at least are less interest to me. The Bayesian versus frequentist definition. Bayesians, who are Bayesians these days? All who use Bayes' rule, or all who use models whose analysis requires Gibbs samplers? I'm not sure. Second, this is anathema, I think, to the ASA, the correct use of p-values and Bayes factors, as opposed to, and I'll give a nod to my colleague, Ben, good scientific practice, which I think is what matters really. I even found a theme which is dead, statistical tables. Now, what are directions of importance are, as I see them? Fostering interdisciplinary interaction. We have to remember that we can play in everybody's backyard, and we should continue to do so. Creating data science as a unified discipline with exploration, prediction in tandem with computation. And I believe confirmation, which is discipline specific. For example, I believe, the whole controversy on p-values and replicability are tied to weak signals. Much less of an issue, let's say, in physics or many other fields. And that's the end of my pontificate. Ask questions.
Would you like to add on
Yes.
in the panel? This was such a so thorough.
They're waiting for their questions.
No, it's like everyone can contribute. It was very confusing.
I thought I gave too long.
Make sure your mic is on. Well, okay, let me ask the next question then. Maybe it will tie in. So I think in this big data era, we have all got very good at explaining that statistics is part of data science to our colleagues and deans and to everybody. There are a lot of people in other fields who do some of the same things that we do. What I'd like to ask is, what are the unique contributions of statistics to data science? What do we do that nobody else does and that they can't do without? What do we bring to the table in your view? Anybody can.
I guess I was asked to start on this. So it's very interesting because Berkeley statistics for the last 8 years have really made the case that we're part of data science. So we succeeded moving into the division of computing, data science, and society. Actually, we're exactly in the phase to explain to the dean how we're different. So I think we need to play both, and both are true. So since the question is about how we're different, and I want to follow up on what Peter said, that Peter says that he does theory. Actually, I think Peter actually does, at least when you talk to him, he does relevant theory. And he might not agree to me, but that's how I see him. And that's where I think the statistics people can play a huge role. It's providing the relevant theory, very coupled with interdisciplinary research. Like I think Jeff's talk yesterday was also an example of that, really get into the science, and Ben's talk today. It's really tried to do the integration. And I think I like to kind of amend what Tukey said, statistics play in everybody's backyard. I think we should play in everybody's front yard. Because we actually have the tradition of getting into science. And also we have the technical and computing. We're really the glue. I think when I first met Ben through Peter, I think I used to call him in front of him, behind him, called him the super glue, right? Because he made many connections among different people. And I think that's the role I think statistician can play, is really care about science equally with the methodology and also the algorithms, and in a way, like Friedman would call shoe leather work. So all of that, I think, is actually our unique strengths, right? That's why I talked to Jennifer Chase. That's actually the argument I've been putting forward. We have some unique history and also strengths. But at the same time, I think we need to embed our skill sets and our critical rigor into the context of modern problems. And we need to really do much better, as Jessica was advocating, and I agree very much, we have to communicate very well and bring what our expertise to the people of like our customers instead of waiting for them to come to us. It's just not happening. And the software, extremely important, embed our algorithm into software and write blogs, which I don't do Twitter, but that's what people was surprised this morning. A collaborator in neuroscience said, well, you don't get your science from Twitter. And I said, well, I still read papers. But things like that, I think, is what we need to move. But I think our traditions here, our carefulness is here. And when we really engage in problems, I think we are really necessary. And I think the whole AI and data science were really proper because we're there. But we do have to change our work and the culture to engage. Maybe I will.
Perfect statement, nothing to add.
How?
Yeah, well, everybody's giving such perfect answers. Why don't I ask one of you to say what, from your position in industry, when you look at statisticians, what do you think, like when you hire a statistics PhD, why is that?
Yeah, I think there are real archetypes in our field in statistics, and you spend a lot of time in graduate school and then in your career working and seeing these things, and maybe don't have a kind of surface level awareness that many people who are doing applied science and data science and thinking about computation and algorithms, they aren't aware of these archetypes. Okay, and so we have a way of thinking about uncertainty that really is sort of differentiates us. And so when I, for example, talk to people who I'm considering as future colleagues, or when I work with our PhD students in our consulting course, I think that, I make a real attempt to capture that attitude of knowing archetypes of uncertainty and recognizing categories of inference problems, and being able to take somebody's messy and maybe not completely unambiguous scientific question, and find a way to move it around just enough to fit it into something that is familiar, where we know what good practical answers are and we know what the assumptions are behind those answers, and we can check them and do the right kind of exploratory data analysis. We encourage everyone to look at the data first, but there's an unbounded number of ways to look at the data. You want to look at the data in a way that's guided towards an eventual attempt to solve the problem at hand. And I would emphasize that that is really special to statistics and to us, that even if you branch out a little bit into machine learning and kind of related fields, there's much less of a qualitative feel for managing and reasoning about uncertainty. And that's something that we can really positively contribute to.
Thanks, John. Thanks very much for actually inviting me to be on this panel. I'm really honored. So, well, I think there is a reason. The question is about our contribution to the so-called data science, field. There is a reason. When I look back, actually, most of the statistics department is in the College of Art and Science. Very few of I cannot think much actually in the College of Engineer. So everyone has mentioned actually we are very good at playing everyone's backyard, trying to help them to use data to answer their scientific questions. Scientific somehow stands out very significantly to me to think about actually when we think about the data science, do we really cover engineer? Maybe, maybe not, but if I think about Twitter, think about Facebook, what are they doing? They are basically using data to make money and maybe make people happy, right? But they are really using data to do something, but not necessarily doing some science. But do we really cover them? Do we really want to play in their backyard? I don't know. Are we good at it? I don't know. So in some sense, for example, Citadel, which is supposed a trading company, but what it really does is analyzing data and based on data to actually putting decision of trading. That's it, right? So not much anything else. It's really manipulate data, learning from data and make decisions. So do we really cover this type of finance as well? So-called data science. This is definitely not science. So to me, I think this data science is much broader than only doing science. We are actually helping. If we are doing this right, we should be able to help everyone who use data to make decisions to do things better. I think that's probably one of the places we can do better. But how to do better, I think it depends on everyone in the community to really push out our strengths and also make our students, our faculty, to be able to do slightly broader things other than only science.
So to follow up on the data science theme, all of those of us who are in academia have seen how excited the students are. There's a lot of new interest. Undergrads want to do data science. They don't necessarily know what it is. They're not necessarily prepared to do it the way we want them to, but there's a lot of excitement. So how do we capitalize on that new level of interest? How do we take advantage of that to broaden the pool of students we work with and maybe turn some of them into statisticians, but still keep it statistics as we just described it? You start, Jianqing?
So I stay at the corner. So
no, I can see you.
Well, so first of all, thank you for the invitation and great to be here. Happy birthday, Peter. I've got much to talk to you. It's very busy days. Yeah, so, well, this is really a great question. Right? So I have been a solo in a department for so long, and our Department of Operation Research and Financial Engineering traditionally has lots of undergraduate students. And I believe the first phase when we have this department, people are attracted by financial engineering. And after financial crisis, everybody become like more data science. So the first thing is like, how do we, and our departments continue to be popular because of data science. And then the first thing is, for me, at least there are two opportunities that I could communicate well with students. The first one is through teaching the first class of undergraduate statistics class. So many of us, indeed, for me, until 2016 and to 1991, when I start teaching, it's really the same material, right? So after 2016, I really add a lot of examples applied to different disciplinaries, more computational based. And I insist that my class should not be stopped at 2-sample t-test, because then students cannot get a chance to see what is my normal life, because they were thinking my normal life is 2-sample t-test or analysis of contingency tables. So I insist that they should have at least multiple regression that got a chance of learning, testing, those kind of concepts, even cross validation, even model selection, where you do polynomial regression or spline. These are very easy to introduce. And I was even a little bit more ambitious. Unfortunately, Princeton had only 12 weeks. I insist give them 1 week on introduction to, data science or machine learning, whatever you want to call. Unfortunately, I had to abandon it because there are only 12 weeks, so much for me to teach. So I think it's very important for when you ask students, what is your future perspective? They always say, I want to do data science, I want to do AI. Very few people say, I want to do statistics, right? So then the next sentence I say, well, so if you have to learn something in undergraduate or even back one more step in high school, so where you should emphasize? So they would say, oh, well, math, right? I say, okay, well, this in the right direction, right? So if you want to do AI, data science, math, so when you do undergraduate students, right? So in addition to math, so you should realize that the data science is not just programming language. There's a lot of, or AI is not just programming language. I'm able to write programs, but you should be able to do like a statistical reasoning. So I try to say to them that statistics is really part of foundational data science. When you want to say data science, not in abstract, but in something but more real. Then you'll see that. And of course, through the teaching, we have to give them, a lot of examples. And now the second case that I have that deeply interact with students is our senior thesis. So through senior thesis, I always say that now you all holding data science skills, right? So let's find some problem to work on. And through that work, they realize more and more the usefulness of statistical modeling and uncertainty quantifications and so on. So I think undergraduate education convinced them that statistics is the first step to data science. I think it's very, very important. And I'm pretty sure there are so many other people here who have way more to say than what I want to say here, but let me just quit here.
Want to add on, Ben? Did you want to add?
Yeah, I think Deb Nolan is supposed to be on the panel. Since Deb's not here, I tried to impersonate Deb.
Yeah, impersonate.
Because I think Deb and Ani or John Dinero will be better to speak about the data science program. Even I was engaged with one particular course. So since 2014, so there have been this attempt to really modernize statistics and computing at the same time. This inferential thinking and computing thinking meet in data science courses. So Data 8 was designed with joint faculty from both CS and Stat department. Ani and Giandiero were the masters of teaching, and Deb and Joe Gonzalez really, I was on the team to do Data 100. So these are huge classes with 1,000 about students. And one phenomenon is really that they also nurturing a whole generation of undergraduate research, like GSIs in Berkeley called, it's UGSI, I think that's how they're called. So they really like each team can have 50 students, and they become a community of people and really become head teachers and do tutoring. So they have different steps. So that really changed the whole landscape of undergraduate teaching. We never use in statistics as many, we never use many at all undergraduate students. And many of them go on to graduate schools, I think, because they actually connect with graduate students much better. But of course, it's pretty heavy teaching, as my two chairs, Sandrine and Haiyan will tell you. It needs to be really a balance. But in terms of from student point of view, actually, I'm a parent of 2 students who gone through this. It's a huge success from the student point of view. And now there's also 1 or 2, I think, Fernando Perez and Mike Jordan from the press have been spearheading, and many people taught. I haven't really studied that, so it's another class. So there has been the foundation, actually the new division. I don't think without the courses, the Berkeley division would have as much argument to the administration. And another signature of Data 8 is being copied by many universities. I think Yale actually used the same curriculum and many other places. Yeah, and Michigan, and has really created both, I think, a teaching culture revolution, also curriculum is like you program while you do statistics. And there are connected classes for Data 8 that you can get to more the mathematical derivations. You have a connector in statistics, you can have a connector in neuroscience, you can have a connector in chemical engineering. I don't know that has happened. So that also connect with respect to how the unique contribution, the tradition of Fisher and Box and people like that is really through these connectors. I think Data 100 will be great to have also such connector classes, but I think it's a human resource problem. And to follow on what Jianqing was saying, that we also have machine learning classes, both CS and stats, and CS have now 2 versions, I think. And when I taught stat machine learning, it's also the same, right? Try to bring the research to the undergraduate level instead of a t-test. And actually I do the machine learning way and go to inference later. You do prediction first because they see what they can do. And then you go to the more refined and introduce very, very carefully a random variable. And I think that's what, I hope I impressed in Deb, okay. Okay. You can ask Deb to watch my video. Yeah.
To follow up on students, so once they do go on to graduate school, and assuming at that point we have convinced them that they're doing statistics, and we teach them a lot of things, some of which they use later on and some of which they don't. Looking back at the many years you've been doing this, what do you think are the most important things for PhD students to learn in graduate school? What really stays?
So this is my turn now. Maybe I should also add, of course, the undergraduate education is very different in Europe. That also makes the programs quite different. But on the graduate level, we're probably more similar also that what happens here. So the skill sets, a bit my personal opinion, I'm not a big fan of kind of telling my students that they should learn a particular skill set, because I think this is really an education, also graduate school. It's a basis for the next 20, 30 or 40 or 50 years. And maybe the landscape will change quite a bit. So, but what I do encourage them very much is point number 1 in graduate school on the thesis work, that they really should try to shape their own research agenda very early on. Of course, I help them. I think it's important to introduce them, but I really would like to see my students developing very quickly somehow their own direction. I think this is tremendously important for further academic career, but also in industry, it's important that you take the lead, you have your own vision, your own ideas. So this is in a way my number 1. My number 2 is in terms of scope. Of course, students are totally different, and that's good, it's great. But I tell them they should go deep in 2 subfields. So they have, maybe they start with one, but I strongly encourage them that they go a bit deeper or deep in another one. I mean, it could be, say, mathematical, theoretical, and also a very applied project, and so on and so forth. I think this is important, it's good, and I think it's also part of maybe the statistical culture that it's broad, right? And so I think this is a very important second point, going deep in at least 2 areas. The third thing, which I think is kind of a skill set, is communication. I think this becomes extremely important. Communication in written and oral form. So this is something a skill maybe which needs to be trained and learned. And so I think this is super important. And the fourth, it has been mentioned already a bit, is kind of team spirit. I think more and more in statistics and in many, many areas in science, it will be done in teams. Also, certainly in industry, I guess. I have never worked in industry, but so team spirit at least. So of course, if a student doesn't want to really do teamwork, at least the student should develop team spirit. And even more so if they do teamwork, that is something I would also strongly encourage.
Peter, would you like to? Yeah, go ahead.
Don't still teach. Go first.
You did a great job. Everything I would have said, you already said, but maybe I'll pick one thing, which is writing. I think essentially nobody writes well when they get to graduate school. I definitely count myself in that category. And so one thing that I really encourage the students I've worked with to focus on is to spend the time to produce a document that you think you're going to be proud of in 10 years. Because, you know, the research you're doing is interesting and there's a chance that people will be reading it 10 years from now. And, you know, I've had the experience of reading something I wrote 10 years ago and cringing, right? So, and you need to, how do you get good at writing? You read a lot and you write a lot. You know, you need to look at, you as an advisor, you can show your students really well-written papers, really badly written papers. There's no shortage of both. And ask them to explain what the difference is. And it's easy, when you look at good papers, they're obviously good. And the same often goes for bad papers. So I encourage everybody, think of it as a skill that is absolutely as important and on par with verbal communication, with, getting research done, et cetera. That's my view.
Thanks, John. So I think if like most of our students go to academic after graduation, then I will just shut up. I will try to provide a slightly different perspective from if I'm in industry, I'm trying to hire some students, looking for some stat PhD graduate. If I want to hire them, what property or maybe help them to get working well in and this industry I work in right now. So what I did is I actually went back to do some sampling. I did a snowball sampling, whatever statisticians are working on my floor. I asked them this question about what do you think is the strength of the statistical training you have get, and also what do you think which might be a little bit better if you want, you hope it's a little bit better. So the strength I got back is, I have a note here actually. So mainly it's a data skill. There are two levels of data skill. One is I guess in-sample data skill. Really, when you deal with data, like how to clean data, how to manage data, how to manipulate data. Those are in-sample data skill. And then there is the out-of-sample data skill, which means you have to think beyond data. Think about confounders and things which you see the data, but those are factors will determine how you get the data, and maybe what will lead your conclusion to be biased away from just your data. So this in-sample and out-of-sample, both data skill are very important for answering questions. At the same time, what they said they hope they can actually learn more or learn better is some kind of computational skill. In some sense, I don't mean you run R package, just through your data into R package, run LM, then you get the coefficient, get p-value altogether. But what they think they want to know more, or what will help them more, is actually to knowing how the package handles the data. If you want to actually build some better LM, how do you do it? And if your data size is so huge, then how do you actually write your code and send your data to parallel computing and run your LM efficiently? So those are the computation skills I think we teach in some degree, but it probably will take a little bit more for the faculty, and also maybe encourage them to go out of our department, go to computer science, go to more more hardcore computing class to learn. They think that will be very beneficial for them. Yeah, I think that for graduate education, probably that's what I learned from my cluster sampling. Again, that's very biased from the one I know. There's lots of other people who don't need it, but at least for the things I see, that's one of the things important.
So I'll ask my last question, and then I'll turn it over to the audience. And this is perhaps the most important one. Traditionally, we focus on our methods and our theory and our applications, maybe data science, but we all know that big data has affected humans, has affected society in very real ways. And many of these ways are good, many of these ways are bad. And we often don't think about it perhaps as much as we should. So how do you see the role of statisticians in mitigating the bad, increasing the good, in terms of the impact on actual human life? It's a tough one.
I'm supposed to start on this one. I mean, you know, to the extent that I talk about practicing what I preach, I think some of the new problems are just the old problems at larger scale, like helping people in one way or another be critical consumers of the stuff they read in the news, the you know, understanding the kind of what at Berkeley we would call the stat 2 nuts and bolts of what's a sensible analysis and what's a nonsensical analysis. We are always going to have a role to play in that. I think, you know, I don't know a field that has as much corporate understanding of causal inference and the difficulties of causal inference as statisticians and maybe biostatisticians. So we're always going to have to take the lead on that. And, you know, certainly Berkeley statistics and Peter and colleagues of many decades have a very long-standing tradition of being deeply involved in those kinds of public policy discussions and in a way that kind of really move the needle. I'm personally not that's not a thing I do, but it's a big part of the Berkeley statistics tradition. I guess there are some also issues that are just brand new, and those have to do with things like privacy and the way that you know, large companies that are acquiring voluminous data sets about the entire population of the US or the world, what actions they take and how they behave. And I guess I haven't reasoned much about exactly what the special role is that statisticians should play as opposed to others, but I'd be curious if anyone else on the panel has, or what other thoughts are. But you know, we as the kind of enforcers of sound scientific method and reasonable causal inferences, we're always going to have kind of that position to take, I think. So.
Maybe I'll add one point. This is maybe just a very small part of statistics. So I just mention a name and then you can connect probably quite quickly. So what David Spiegelhalter does, the communication of numbers of risk. I think certainly during COVID, this had a huge impact, but also before, I mean, he had a big impact on the medical health system in the UK. It's really only explaining to the public, to the decision makers. It's a small area, I think, in our field, but some people have engaged very much and with much success. And I think that's great and it's very important. And this is something which I definitely see as a task where statistics had an impact on society.
Yeah, just to add to what has been said, I think it's very interesting. I was on the causality program at Simons here, and they actually invited a lawyer who studied fairness, because a lot of the fairness question have been framed through the counterfactuals. And they actually invited lawyer to be part of the program. So there was a lot of interactions between social scientists, somebody who know the legal rules, and with the causal inference people. I thought that was a very fruitful discussion. I get to talk to her and many others. So they also, in terms of what John was talking about, written communication, they also had like science writer in residence continuously, and they have theoretical speaking series, which is broader. So I think those are the things we can really learn from the computer science community. This is mostly, and if you look at the 10th anniversary celebration last week, and they really, this is called Institute of Strategic Computing, right? Theory is actually in there. But the breadth of talks they have, I think they take a very expansive view of strategic computer science. And I think that's something we could also do, that take a very expansive view of statistical, even mathematical statistics. I think eventually it's, I would call it globalization, right? Of fields, not countries. And it's healthy. And in terms of the graduate students, I think it would be nice if we have ASA or have a camp, talk to speaker, right? To have him to really train the next generation of people how to communicate. And I think those are all the things young people can ask IMS to do. I think we have the IMS president here. And oh, you're the past, but you can pass to the next president. So I think it's communication and engagement. We closer to problems, I think will really benefit the whole field, and to show, well, basically have to prove we are useful.
Let me add something to topic number 4 on graduate education, just slightly change a gear. So I'm always tell students a very simple sentence, but which is not really quite true. I say, learn how to learn. I learned from Peter. I think what I'm doing now is very different with Peter when I was a student here. So, I mean, learn how to learn is important, but from my own collaboration with, let's say, economists, in particular, the area, right? So nowadays, data is everywhere. So in the education part, we probably didn't emphasize as much to collect data ourselves. So there's a lot of database. I mean, UK Biobank, I mean, all those newswire data is all there. So we didn't really teach students as much and encourage them to find different data. So my own experience is like we were trying to use nightlight data to predict the housing activeness in Pudong. And after we working very hard, outer sample R-square is still pretty low. So we realized that, the bright area could be airport, could be other, right? So it's be very useful to look for, let's say, land planning data, give you an idea to further deconvolute these kind of confounding factors. So when I'm working with economists, they are very easily, when something doesn't work, they're looking for new data. We were educated, when something doesn't work, working very hard on a different learning methods. And that attitude need to be changed somehow. So this, I just want to add a little bit to that. Yeah.
Yeah, I just want to amplify this, learn how to learn. I think that's what we try to do. And also in terms of interim research, Berkeley has a tradition of 215A, many generations. And I have the fortune to have been teaching in the recent time. And I know Liza brought it to Michigan. So I think,
but we
yeah,
have it, yes.
But I think this is something, it's a more scalable way than just one-on-one coaching.
So thank you all very much. So great to listen to all the answers. I'd like to turn it over to the audience now. Just raise your hand and I'll pass the mic over.
Thanks, Liza, and thank you all for a wonderful panel. Really enjoyed all the comments, and I just wanted to follow up about 2 of them. So one of them is the Bin's point about the central role that education has played in building this new division of data science. So there's an upcoming workshop national workshop on data science education. It's at the end of the month, June 27th to 30th. It's hybrid. So basically diving deeper into all the courses that Bin has described. And then the second point about John made about the importance of writing. Even if Deb was here today, she probably wouldn't have said it, but Deb wrote a book about writing, and it's on David Aldis's list of highly recommended books. So, you might want to take a look at that. So just advertising for Deb, who's not here
Good
today,
product placement.
So. Excellent.
So I just wanted to expand a little bit on something that Peter mentioned in his opening comments about the importance of facilitating interdisciplinary interaction. And I know Ben mentioned, like writing blogs, being on Twitter, and the importance both of statistical knowledge diffusing into other disciplines, but also knowledge from other disciplines diffusing into our own. In order to know that you're doing relevant theory, you need to have some notion of like what theory might be relevant. And as someone who came to statistics from outside, it can be a very intimidating temple to approach. And so I'm curious if you can comment, there's ways to do very, very focal interaction, right? That I think we do well, and maybe we can do more of, where you can really influence science, a very specific scientist. But what are the things that, we're maybe not thinking about enough in terms of the conferences we go to, the venues that we publish in, the ways that we communicate? What are the things that we do well that we need to do more of? And what are the things that maybe, we aren't really on our radar in terms of the way that we fruitfully interact with other disciplines?
Like I might give a shot. So I think the blog, I think maybe the community, I know Andrew Garman does a blog, there are a couple of people who actually does blog, but relative to other field in data science, we have fewer bloggers. So one thing I think maybe people can do is really get the whole team of bloggers, because it's hard to keep pushing things. But if you have a team of bloggers, then the Berkeley AI lab, we have taken advantage. They have a blog. We just, if you have time, we send a few things and also diffuse into the AI machine learning group at large. But I think statistics would be nice to have more blogs with more bloggers than just personal blog, which have been really helpful already. I think, I don't know about Twitter. I feel like it's too short, right? Sometimes it's just too soundbite. So I think maybe young people can organize a blog together.
Hello. Yeah. One thing I think, statisticians bring to the table is when I work with people in the medical school, for example, often someone will come to me and they say, oh, they've been trying one of the new techniques like deep learning or neural networks on their data, and they got a little bit stuck. I think one of the things we have to offer is we have a whole broad range of tools. We should know about the new tools. But a lot of the time, some of the simple tools that we've used all along just do just a fine job. And if they do, they're much easier to understand and to work with. So bringing the whole range of statistical tools to the table and showing you don't always need to use these new sexy complicated tools, but there are places where they're useful. I think that that brings good value to the table, especially these days where people are asking for explainable AI, right? They want to eventually interpret what they're doing. So I think that's something we can contribute a lot.
Question, Trevor?
Yes.
Oh, was it supposed to be a question?
No. No, it wasn't.
Do you agree?
Anybody wants to speak? Peter, would you like to say something about
I have a
simple
funny
things?
comment. Oh, sorry. Let's have your hand. Please.
Talk about, but I still don't understand.
Okay, I'll come back to
What
that. Hold on, Karen.
What are the
Karen,
tools? What are the tools a student should be asked to learn to get a degree in data science? How much statistics, how much calculus, how much computation? Does anyone have a clear idea what kind of tools they should have to get a degree in data science?
Yeah, that's the first question.
Anybody wants to try and answer them?
Well,
What should a degree in data science be?
Okay, I mean, to answer that question, I think this is almost a political issue, but there is some argument for picking, I mean, given that we have this glue function, which we all agree with, trying to actually, just as a label, identify statistics with data science, not have competing data science and statistics degrees. And I have to admit this, it's sort of a trivial reason, one trivial reason. Statistics, unfortunately, I mean, one of the reasons that attention is only now being drawn because of machine learning and so on, is that we have a little bit had the reputation of economics, right? We're the dismal science. We're the people who always tell you, be careful about this and that. And although this can be useful, people don't like, on the whole, to be told that their latest discovery is worthless. So I think possibly a relabeling in which, all these roles we've been talking about are assumed is worth doing if you can try. It also has the advantage of, I think, perhaps giving easier access to influencing policy. I mean, it's a vague comment, but
We'll have the next question here.
Hi, I am Jitendra Malik. I'm a computer scientist who works on things like computer vision and machine learning. So I'm going to ask about a question about that. But first, I want to make a comment about Peter. I got to know Peter in the 1990s when we had a joint project on transportation. So Peter called himself a theoretician, but this was a project which was on questions like, how long will it take to go from Berkeley to San Francisco on the Bay Bridge at 8:15 a.m.? So I just want people to know that there are very practical things that we worked on together with John Rice, I don't know if he's here, and Praveen Varaya and others. So, but at that time, the questions were about machine learning. I mean, data science was not a term then in the 1990s, but I learned a lot from Peter and from his students, and Liza, whose committee I served on. So, of course, last 10 years have been very big in this field and under the label of machine learning. And of course, the business of Google and Facebook and Amazon rests on this. As a person on the machine learning side of it, I have a little joke, which is that we just know how to give terms. We take the terms that statisticians have and give it a much more sexy label. And as a result, there is this so-called ML bump, right? Machine learning is worth $10,000 on the job market for sure, just if you can claim that. But anyway, that's a joke aside, but there's a substantial question. The substantial question is, to me, goes back to, I think, Leo Breiman's article on the two cultures. And I think at Berkeley, we have not had a conflict between statistics and computer science. We have had people with joint appointments. I think we have worked very nicely together. But the substantial questions in Leo's article from 2001 or 3, something like that, was that practical people don't care so much about the probabilistic model. They care a lot about prediction, and they have these prediction questions. What's going to be the price of a house? Is this bird robin? And so on and so forth. And people like me, we ran with those. So I teach an undergraduate machine learning class. The difference between my class and the class that my statistics colleagues will teach is I talk all about these cool applications, machine translation, recognition, robotics. And we get those students. They come to us. We seduce them. Okay, So and I think that, but we are in this together. So we should really work together. I think the fields are really. It's all, the intellectual space is totally a continuum. So anyway, this is a comment, but to make it into a question, what do you think of Breiman 20 years later? And what does it tell us about what we should be doing today? Because data science is a label. I think the substantial questions are the same as 20 years ago.
Yes. Great question. Yeah, two cultures 20 years later.
Yeah, so that paper came out right at my most, persuadable and influenceable moment as a PhD student in statistics at Berkeley, working with Mike Jordan. I had come to grad school specifically to think about kind of the connections between statistical inference and computational approximations. I was excited about all those topics, and Leo kind of wrote this paper saying, yeah, that's it. That's everything. For just predict and don't worry about parameters. Their parameters only exist in your mind. And, and I think that, the messages of the Two Cultures paper were borne out in the sense that you can get a lot more mileage out of non-parametric tools for building prediction rules than you can from low dimensional parametric tools for building prediction rules. That is kind of, this is in full acknowledgement of Trevor's point, which is not always, but at least sometimes you can. Sometimes the complexity actually helps. On the other hand, I think what I came much better to appreciate through taking 215 and through interacting with people like David Friedman was that there is another slice of statistics about causation. And if you're solving a prediction problem, that's great. You're solving a prediction problem, but prediction problems are really qualitatively different than causal inference problems. And the Two Cultures paper, I think, doesn't have a lot to say about causation. And there was I don't know, I wouldn't call it a sin of omission, but Leo was out to make, I think, in my view, a very particular point about the efficacy of different approaches to solving prediction problems. But in the course of doing that, he gave an account which could be misunderstood as an account of all of statistical culture, right? And there is more going on in statistics than explanation and prediction. There's also causation. And I think it is just a different category. So I would say, Leo was right about many things in that paper. My view is that it was the points that he wanted to make were largely borne out, but he was silent on points that I think the discussants even of that paper were already raising about what he didn't even address.
The only thing that I would disagree on is that you lumped prediction in with explanation. And I don't think it's the same thing. In a way, prediction is certainly something that we all value and which is a criterion of goodness. But in order to develop things, right, to go to the next level, remember in Ben's thing, this arrow going backwards, you have to be able to interpret, understand how it is that you've been successful in prediction in order to improve that prediction in others. That's different.
Okay.
Okay.
David Cox actually wrote to this statistical science article in the discussion, the prediction should be validated in new contexts. And that is a robustness question. It's very much tied to the causal question. And of course, if we look at prediction in the broader context, like in economics, the prediction of a new policy, of course, that is a causal question. The experts know that. But I think sometimes when people talk about prediction, it's a much broader context. And I think even people in causality would be happy if they can predict an intervention, whether this is now really causal or not, that's not so important, but that would already be a big step forward. So I think I sometimes argue a bit, well, yeah, prediction, but prediction, the usual thing, what we have in mind, okay, it's our f hat x, right? But of course, in the next broader level, it becomes much more an explainable issue and a causal issue. So I just want to make that comment.
Causal, I think there's also things I read about a definition causality. I like quite a lot, kind of along what Peter was saying, is that the causality is really evidence so that you can act on it. And that kind of move away from the mechanistic, but it's become evidence driven and also can be evaluated even without a mechanism. But I think we kind of go back to a full circle, right? We went to machine learning, or machine learning people took things and made new names. And now the machine learning people are doing experimental AI. And I think it's a great time for statistics people saying that, yeah, we can do it with you. And we have been here well, much longer time. But the key is there are newer problems that even we say that logistic regression is interpretable, but it's not if you have a million parameter in logistic regression. So if you work with the ER doctor, right, decision rules are interpretable, but for ER doctor, they probably only want time split. But if you do preventative medicine, then you can have maybe more decisions. So a lot of the context also matters. And we cannot just say that, well, decision are interpretable, therefore we're done. So it's really the specifics will drive the next generation of interpretability and then bring our skills to solving the problem and really bring a lot of things back to statistics. And then I think the field will really be very prosperous.
Well, I think this is actually a great question on which to end. Thank you all for participation. Let's thank all of our panelists. So